Okay. If we were to consider the area bounded by the curve and the x-axis, basically look something like that area right there, what would happen is that I would look at it and say, I don't know what geometric figure that is. When I took geometry, I didn't memorize a formula for finding the area of such a thing, but what we do have is a way to rewrite this integral and break it up into smaller pieces and evaluate the little integrals, and each of those little integrals, maybe there's a geometric figure whose area we do know how to calculate. So I would write this. This is the integral of, or the integral from 0 to 2 of 3 dx plus the integral from 0 to 2 of 2 times the square root of 4 minus x squared dx. Now 3 dx, we can handle that because that's just a horizontal line. And the area bounded by a horizontal line segment, and the x-axis is going to be the figure is a rectangle. It's easy enough to find the area of a rectangle. We still don't quite have it here because 2 times the square root of 4 minus x squared is not going to be a semicircle. It's going to be a stretched semicircle, basically the top half of an ellipse, which is a much more complicated formula that we don't memorize in high school geometry. So one more time, it's going to be the integral from 0 to 2 of 3 dx plus 2 times the integral from 0 to 2 of the square root of 4 minus x squared dx. And then it's not so bad. We can do this. In fact, we did do this in the previous example. This much was pi. The integral from 0 to 2, square root of 4 minus x squared dx. We just got through doing that, and that's pi. The first one, though, to find that area, 1, 2, 1, 2, 3. It's the horizontal line segment, y equals 3, and we want the area bounded by the y-axis and x equals 3. So that's 2 times 3, which is 6. So the area bounded by that horizontal line segment and the x-axis between 0 and 2 is 6. So it's going to be 6 plus 2 pi, which is going to be, what, 12.28 something? 6.2 pi. So back to the graph. Second calc value. I should have just gone 0 to 2 previously. Second calc integral. It's just the right half of that thing. That's the integral it should be. 12.28, and this is about what we have with 6 plus 2 pi. That's the area that it wanted. When I drew the picture earlier, I went all the way from -2 to 2, and I should have just gone from 0 to 2. Let's look then at 5.4. Fundamental Theorem of Calculus Part 1. There will also be a Fundamental Theorem of Calculus Part 2. Fundamental Theorem of Calculus Part 1 is going to be a way for us to use the idea of the antiderivative to write, actually, to make a direct calculation for the area bounded by a continuous curve and the x-axis over a bounded interval. Let's look and see what it says. If f is a continuous function on the closed interval AB, and if big F is any antiderivative of little f on that interval, then the integral from a to b of little f of x dx can be obtained, well, how? Let's see. Taking that antiderivative and evaluating at the upper limit, evaluating at the lower limit, and then just taking the difference. So little f So here's a function, something like that. And that's y equals little f of x. And we want to know, what is the area bounded by the curve and the x-axis? Well, according to the fundamental theorem of calculus part 1, if we can find an antiderivative, recall that the integral, the indefinite integral of f of x dx equals big F of x plus c, such that big F prime of x equals f of x. That is, we're looking for a function that we can take the derivative of and get our original function f as the answer. So if we could find the antiderivative, well, if we take the derivative of to get to little f, if we have big F of x and we find big F of b minus big F of a, that's the area. In fact, I might have just put it right in there. Big F of b minus big F of a. That's what it is. Fundamental theorem of calculus, part 1. Not going to share the proof with you, but let's look at some examples and see if we can see if this is a meaningful thing to do.
So f of a and f of b are both like equations?
Well, I guess I need a concrete example to show what we mean here. They're functions. Let's look at this. Let's look at x squared and see what big F is going to be. Little f is x squared. Little f is x squared. So little f of x is x squared. What we need is a function big F of x that we can take the derivative of to get x squared as the answer.
Oh.
What can you take the derivative of to get x squared as the answer? So we got to think backwards. It's got to have a higher degree. And so that when I multiply by 3, I get that 1 there. So many thirds, something like that. Would it be that? If I take 3, then I would have 3/3 x squared. So the 3's would divide out and we would be left with x squared. So x cubed over 3 is the big F. That's what it is. Now, it's not unique. If we were doing the indefinite integral, the integral of x squared dx would equal x cubed over 3 plus c. X cubed over 3 plus 5, x cubed over 3 plus 19 would also work as valid antiderivatives. Usually it's best to go with the simplest one, because what's going to happen, and we should probably look at an example of this, what's going to happen, since we're going to evaluate it at 10, we're going to say 10, show all my work here, we're going to say big F of 10 minus big F of 4. We're going to say 10 cubed over 3 minus 4 cubed over 3. If I had thrown in some other constant, like thrown in a 19, it would have been 10 cubed over 3 plus 19, but then we'd subtract 4 cubed over 3 plus 19, and the 19s would cancel. So I could have used a 19 or a 5 or a pi or whatever, but they would cancel. So it really, although any constant would work, the nicest constant is 0. So that's the one I use. So 1,000 cubed minus 64 cubed is going to tell us the area bounded by this curve and the x-axis. So I'm thinking 9, 3, 6 over 3, and that's got to be divisible by 3, huh? Maybe 3, 1, 2. There we go. 312. 312. So x squared goes pretty high in that interval. Let's see what it looks like on our calculator. Y equals just plain old x squared. And since if we go all the way to 10, it's going to go as high as 100. Let's increase the y max, maybe more than 100, maybe 150, and the y scale to 10. And we don't have to go quite that far to the left, maybe -3, something like that. So this should fit this portion of the graph comfortably on the screen. If we go -3 to 10 along the x-axis and -10 to 150 along the y-axis, I think we'll see a decent picture here. Graph. Okay, maybe I could have gone higher, but we want the area from 4, 1, 2, 3, 4 to 10. That's the area. If we were to look at all of this, that would be, how much would that be? That would be 60. No, it would be 6 times 100, so that would be 600. But we're saying the area of just the red region is 312, a little bit more than half of what we would have in this great big rectangle here. And I think that's reasonable. If I go second calc integral from 4 to 10, it shades it and agrees with us. 312 is what we get for the area there. So we're just finding an antiderivative. Any antiderivative will work. Evaluate at the upper limit, evaluate at the lower limit, subtract. That's the area. X squared plus 1. Does this really offer us that much that's new? Maybe a little bit new because we have multiple terms. Also, some notation that's going to be useful for us for doing this evaluation, I think would be good. So not a lot new here, but a little bit. The notation where we want to write the antiderivative to keep everything as neat and clean as possible, I'm usually not going to go off in the margin and say, okay, big F of x equals. No, we're going to put it in some brackets. We can integrate term by term. If we feel good about x cubed over 3, we can put that much in there. Plus x, take the derivative of x and get 1. We can toss in any other constant that we want, but I'm just going to leave it 0. And this would be an antiderivative for x squared plus 1. As far as the 2 and the 6, what I want to do is carry those over, just kind of scoot them sideways, and put the 2 here and the 6 there. What that tells me is I'm going to take the 6 and I'm going to plug it in. Substitute it for x in both those places and evaluate that. And then I'm going to take the 2 and plug that in to both places, get an answer, and then I'll subtract what I got from plugging in the 2 from what I got from plugging in the 6. So it looks like this: 6 cubed over 3 plus 6 minus 2 cubed over 3 plus 2. So I'm not calling it big F of x, but it is. It's the antiderivative that we're evaluating at the upper and lower endpoints. And there are probably nicer ways of doing this. I'm going to have so many thirds at the end, it looks like. But here, if I said 6 cubed is 216 and divide 216 by 3, I think that's 72. I think I want to call that 72 plus 6 minus 8 thirds minus 2. Without a calculator in hand, that's as nice a way as I can think to do it. And then 72 plus 6 equals 78. 78 minus 2, 76. And 76 minus 8 thirds equals 70. What do I want to do here? I don't know what I want to do here. 73 and 9 thirds. Minus 8 thirds. Would it be 73 and 1 third? Maybe. That looks really strange though. X squared plus 1. Graph that. Here we're just going from 2 to 6. So second calc, 7, lower limit 2, upper limit 6. Yeah, 73 1/3 is what we get there.
On a test, you want to show us the work, or you want to do nothing?
I want to see this. That's big. And I kind of want to see maybe a step there so you knew what to substitute. And then the next thing I'm looking for is that. I really don't, I say that, I hate to use the expression, I don't care, but it's not going to be a big deal to me. What happens in between? I want to see the antiderivative. I want to see that you knew to substitute into the antiderivative, and I want to see the final answer. Yeah. From there to there, get there the best way that you can. Just punch the whole thing into a calculator if you like. But I do need to see the antiderivative. Sine function. I like this one. I think this is really, really interesting because I think of sine functions, transcendental function, and going from 0 to pi. 0 is certainly rational, but pi is an irrational endpoint. But the area, when we graph this, y equals sine x, and I'm going to zoom, let's see, I'm in radian mode, I'm going to zoom trig, have it look like this, just going from 0 to pi. We're trying to see what is the area bounded by the curve and the x-axis right in there between 0 and pi. It looks like it's positive throughout, so it's just that area, whatever it would be. So we need an antiderivative for sine x. What can we take the derivative of and get sine x? Negative cosine x. Take the derivative of negative cosine x, and that does it. So we need to take negative cosine x, evaluate it at pi, evaluate it at 0, and subtract negative cosine pi minus negative cosine 0. It helps to have parentheses there too. Feel free to put them there as well. Not as big a deal. Negative cosine pi minus negative cosine 0. What's the cosine of pi? It's negative 1. So it's the opposite of negative 1 right there. Minus, goodness, I feel like I still need those parentheses. What's the cosine of 0? It's 1. So the opposite of 1.
So the answer is 2.
I think it's 2. I think it's 1 plus 1. It is 2. So the area bounded by that half of the sine curve and the x-axis, if we do the second calc 7 thing, from 0, the upper limit, to pi, 0 is the lower limit, pi is the upper limit. The area is exactly 2. I would have expected something irrational, but it is exactly 2 right there. What if we go from 0 to 2 pi? It's going to be 0. The total area bounded by the curve and the x-axis would be 4. But the 2 up above and the 2 down below will offset each other, and it's going to be 0. And you can see what goes on here. It's negative cosine x from 0 to 2 pi. It's going to be negative cosine 2 pi minus negative cosine 0. Well, the cosine of 2 pi is the same as the cosine of 0. So it's going to be negative 1 minus negative 1. So negative 1 plus 1 is going to be 0. So if we redo it, second calc 7, 0 for the lower limit, 2 pi for the upper limit. What did I do?
Keeps on giving me an error.
Second calc. Oh, I think I know why. When it does the zoom trig thing, 2 pi is just a little bit more
Okay.
than the right. If I'd go 6.28, it'd probably be okay. I think the thing to do See if I go to the window, yeah, 6.15 is a little less than 2 pi, so it's outside of the window range. If I go 6.3? 522.856, that should work. So a little bit more than 2 pi there. Second, calc 7, 0, 2 pi, and then 0. The net signed area is 0. Now, if we wanted total area, we could calculate the area above, we could calculate the area below, and we could add those areas together. If we want the calculator to do it for us, the thing to do oops, could make it go on the inside. Take the absolute value of the expression. I guess the older calculators I could have gotten by with that. ABS is what you're looking for on the older TI-83, the TI-83s or the older TI-84s. ABS of the expression sine of x. Close the sine of x in the parentheses after the ABS. It's, what is it, math, num, math, press the right arrow to go to the number menu and the number 1 on the list for ABS. If you graph the absolute value of the sine of x, ABS of the sine of x, what the taking the absolute value of a function does, anything above the x-axis it leaves alone. Because it's positive, the absolute value of a positive number is that number. But anything below the x-axis gets reflected about the x-axis and ends up above the x-axis. So the graph looks like this. There, just like that. So if we now integrate from 0 to 2 pi, second, calc 7, 0 for the lower limit, 2 pi for the upper limit, it should count them both positive, so it tells us the area is 4. So if there's an application where we need not the net signed area, but the total area bounded by the curve in the x-axis, then that's the absolute value of the function. Trouble is, it's tougher to come up with an antiderivative for the absolute value of something like that. It's just not. We usually have to break it up into little subintervals if we want to do that with an antiderivative. And I don't want to slight the exponential functions and logarithms. So just so we remember how to find those antiderivatives. The integral of 2e to the integral of 2e dx between natural log of 2 and natural log of 5. I've chosen the limits of integration so that it'll be easy to evaluate e to those powers. Need an antiderivative for 2e to the x. What can I take the derivative of and get 2e to the x? Would it be 2e to the x? Sure enough, the derivative of 2e to the x is 2e to the x. So any constant times e to the x is going to equal its derivative. So we take 2e to the x and integrate from natural log of 2 to natural log of 5. Sorry, I'm not integrating between there. We're simply evaluating 2e to the x at natural log of 5 and 2e to the x at natural log of 2. So it's going to be 2e to the natural log of 5 minus 2e to the natural log of 2. So 2 times 5 minus 2 times 2, 10 minus 4 equals 6. So it's nice because the limits of integration maybe weren't so nice. E to the x and 2e to the x are continuous everywhere, so there wouldn't be any issues regardless of the limits of integration there. There could potentially be issues with the b part. There's some talk of improper integrals in Calc 2. And in a discussion of improper integrals, we have to consider that there might be a vertical asymptote, what to do in case of vertical asymptote, that sort of thing. Fortunately, there's no vertical asymptote here between 2 and 5. Vertical asymptote happens at 0 for this particular function. So we stay away from 0, and we don't worry about it. So all we need is an antiderivative. What can we take the derivative of and get 1 over x? Is this the weird one? If we have x to the negative 1, and we add 1 to the exponent and then divide by that new exponent, bad things happen, right? So we don't want that. But this is the special one. This is special, so we can't do it that way. But we know if we take the derivative of, is it that one?
Yeah.
Is that right? Yeah. Derivative of natural log of x. Now I could get by with just the x because I know my limits of integration are positive. But if my limits of integration were negative, it would still make sense to do this. Because 1 over x is good for positive values of x, and 1 over x is also good, is also good for negative values of x. So I'd like to be able to do this for negative values of x. So just in case in a future example, it's like negative 5 to negative 2 instead of positive 2 to positive 5, absolute value about the x, and this works as well. All it does is double the domain and enables us to deal with areas over here just as well as we can deal with areas over there. So in this case, it's an area over there. So natural log of the absolute value of x, we're going to evaluate that at 5. We're going to evaluate that, let's erase that there, evaluate it at 5, evaluate it at 2, subtract. So natural log of the absolute value of 5 minus the natural log of the absolute value of 2, which is the natural log of 5 minus the natural log of 2. If we wanted, I suppose we could say the natural log of 5 halves. Or maybe just punch it up on a calculator. So a couple of ways we could do this. We could say the natural log of 5 minus, whoops, close the parentheses, minus the natural log of 2, and get 0.91629 something. If we graph it, 1 divided by x, zoom 6, not the best viewing window, I guess, but second calc 7 from 2 to 5, that's about what we got, 0.9162 something.
So even if you would do the negative on that, would it be the same, it'd still be the same area, right? So like you had the negative 5 and negative 2, you could still get the 5 and negative 5 and 2, and it'd still be the same area for both sides, right?
I guess the thing to do is consider this. Suppose it was this.
Yeah.
I think the fact that the negative 5 comes before the negative 2 is going to make it negative. So we call this the C part. C part 1 we just made up on the fly here. The integral from negative 5 to negative 2 of 1 over x dx, it's going to be this area down here. This would be natural log of the absolute value of x going from negative 5 to negative 2. It would be the natural log of the absolute value of negative 2 minus the natural log of the absolute value of negative 5. That's the natural log of 2 minus the natural log of 5. But I want to say that's equal to negative 0.91629. Because it's the opposite of what we got right there.
And that would work out every time, it would just be the negative, right?
Yes. Yes. And we get that, I guess, because of the symmetry. Beware of vertical asymptotes. Okay. 1 over x squared. This has a vertical asymptote at 0, and we're integrating across 0, so this really should not make a whole lot of sense. This should be really kind of bizarre. So if we tried, we would get what? We could get x to the negative 1 over negative 1 from negative 2 to 1. That would be negative 1 over x from negative 2 to 1. It would be negative 1 over 1 minus negative 1 over negative 2. It would be negative 1 minus 2, which is, no, minus 1/2, which is negative 1.5. However, there's 1, there's negative 2. This function is never negative. 1 over x squared. 1 over x squared is always above the x-axis. 1 over 1 squared is 1. 1 over 1/2 squared is 4, I guess. So it looks like that. And it comes down and looks like that. And that. So we're wondering, what's the total area here? Negative 1.5. Negative 3/2. No, that's nonsense. So that's just not going to work. This is well, we'll call this positive infinity at some point, but I'm going to say it's this is not finite. Not finite. I mean, it might be interesting to see what GeoGebra does with that. I think I've done something similar to that. Area bounded by the curve, because it tries, but it just can't seem to agree on anything. So open, let's go area under a curve. If we let that curve be 1 over x squared, come on. 1 over x squared looks kind of like that. And suppose I want to go from, well, 5 I guess is good enough, negative 2 to 1. Okay, exact total area, negative 1.5 is what it got. But what kind of sense does that make? Well, if we increase the number of rectangles, maybe for this number it looks like 20.59, or maybe it's 68, or maybe it's undefined, or maybe it's 99, or 121, or 112, or undefined, or 266. It's just, you'd think it'd be approaching some number, a limit, if it actually existed, but it's just all over the place. And in fact, depending on where we choose the endpoints of these rectangles and exactly what points it picks and calculates, we could make this just as large as you want it to make. So ultimately it will make sense to call it positive infinity. So yeah, it doesn't know what to do with that. Example 6 looks terrible, but really it's not. Example 6, what's it going to be? We can find an antiderivative. We can plug in the 4. And then we can plug in the 4 again. And then subtract. We get 0. Yeah. So that's 0. Simply because the upper-lower limits are the same. Short, sweet, that's 0. The B part is not as short or sweet. There's some calculating that has to be done. But if the graph is above the x-axis between 2 and 4, this value is going to be negative. All the area is going to count negative because the lower limit is greater than the upper limit. So if I want to visualize a picture of a graph that's above the x-axis, what I could do is this, negative the integral from 2 to 4 of x cubed dx. And I could evaluate the area that's above the x-axis and then multiply by negative 1 at the last minute. Or I could take the negative sign and put it inside, visualize a graph that's below the x-axis, y equals negative x cubed, and then don't multiply by negative 1 at the last minute, just leave it negative. But the answer is going to be negative, let's go ahead and find the antiderivative. X to the fourth. How does it go? X to the fourth over 4. We're going from 2 to 4. I'm going to try to remember to multiply by that negative sign. So it's going to be the negative of 4 to the fourth over 4 minus 2 to the fourth over 4. So it's the negative of, I think these are both whole numbers. I want to say 4 to the fourth over 4 is 4 to the third, 4 to the cubed. 4 cubed, 64. And 2 to the fourth, 16. And 16 divided by 4 equals 4. So I want to say this is negative 60. Negative 60. You can try it with y equals x to the third power. Zoom 6. Y equals x cubed. We're not going to see it. We're not going to see it. 4 cubed is 64, so the y max probably should go as high as at least 64, maybe 100. Y scale of 10. Now maybe we can see it. Second, calc 7. If we go from a lower limit of 4 to an upper limit of 2, it shows us the area, but it multiplies by negative 1 because I reversed the upper and lower limit. So it's negative 60. This is a real pain to watch. I don't want to inflict this on you. I just want to kind of talk through it. It's rough looking. There might have been a nicer example, but I included all the details in here. I think the picture probably would be good as well. Let's look at the parabola basically that we want to see here. Y equals x squared minus 4. Zoom 6, and then I'll probably need to adjust this viewing window a little bit. From negative 3 to 4, can just about go as high. Second calc value, I'll plug in 4, does that go? Oops, 4. What did I do? Second calc 1. Now plug in 4. And that goes just above the top of the viewing window, so let me set the x max maybe at, y max at 20 instead of 10. A little bit better there. Now, if I want to integrate the absolute value of this expression, and I want to do so using antiderivatives rather than using the calculator, I don't have an antiderivative that works all the way from negative 3 to 4 with a single algebraic expression. I could break it up into 3 separate algebraic expressions and define a piecewise antiderivative, I suppose, but it's going to be hard to do that, and because when I evaluate try to find the area, I'm just looking at the far right and the far left, so any piece in between, it's going to get ignored. So I want to do this in 3 parts. I want to say it's what's going on between negative 3 and negative 2. It's what's going on between negative 2 and positive 2, and it's what's going on between 2 and 4. It changes sign at negative 2, and it changes sign again at positive 2. So if we can just consider this on the intervals where it doesn't change sign, then we could ask ourselves, okay, is it positive on those intervals, or is it negative on those intervals? So a quick sign graph. Let me zoom out. That still didn't help. Zoom out some more. There. Barely. So a sign graph for f would look like this. It's equal to 0 at -2. It's equal to 0 at +2. And we know what the graph looks like. We just saw it. It's above the x-axis up until -2. It's below the x-axis between -2 and 2. And it's above the x-axis to the right of 2. So if I want to write this as a piecewise function of polynomials, that is, try to write it so that it doesn't involve absolute value, I have to do 3 different pieces. If x is less than -2, it's equal to itself, because it's positive. If x is between -2 and 2, it's the opposite of x squared minus 4, because the function we actually want to evaluate this integral for is not this, but what? We're finding the integral of the absolute value of this. So math, num, abs, x squared minus 4. There we go. So we take the little bit that was below the x-axis, reflected about the x-axis. So if I want a piecewise defined polynomial that, or a piecewise function defined using pieces of polynomials, it would look like this. It's equal to x squared minus 4 to the left of -2. Between -2 and +2, it's the opposite of x squared minus 4. Got to flip it about the x-axis. And from 2 on, it's equal to x squared minus 4 again. So if I'll just break this integral down into the pieces from -3 to -2, and then -2 to 2, and then 2 to 4, those 3 pieces, I've got a polynomial on each of those pieces, and I know how to find the antiderivative of a polynomial. Maybe not the absolute value of a polynomial, but I know how to find the antiderivative of a polynomial. So if I do this in 3 separate pieces, then it'll work. And I did it. There it is. You can kind of sort through the details. I use this integral from -3 to 4. I go from -3 to -2, -2 to 2, 2 to 4 of that same expression all the way across, the absolute value, and then on each of those little intervals, I'm able to remove the absolute value. On the 2 intervals on the outside, the expression's positive. So when I remove the absolute value, nothing happens. Absolute value of an expression that's positive is just that expression. The absolute value symbols vanish there, and it's just nothing happens. From there, nothing happens. But when they vanish in the middle, x squared minus 4 is negative between -2 and 2. So when those absolute value symbols vanish, we need a negative sign. So the negative sign shows up. The absolute value of that quantity is the negative of that quantity because that quantity is negative. And from that point on, it's just a matter of finding the necessary antiderivatives, plugging in the top, the bottom, upper limit, lower limit, subtracting, and we end up doing that several times, I guess a total of 6 times, and we end up with 23 2/3 for the total value of that.
So this one's not going to test?
It's a little bit lengthy.
Yeah.
I think it's good for something in the notes. It might even be a good homework problem. But as far as something on the test, I think it would be a situation where there's an application and you look at the application and you realize, oh, this is the integral that I need. And then when you get to this integral, then you ask the calculator to do it. Basically, second calc 7, -3, enter 4, enter 23 2/3. Right. I mean, that's the way I think we ought to be spending our time. Now the example might be, under what circumstances would we need to integrate the absolute value of an expression? And there's a specific type of example that I have in mind when we have to know, oh yeah, that's what we need. Not the expression itself, but the absolute value of the expression. And then once we make that connection, then we write it down, then we go to the calculator, and we save ourselves all of that. Because that's a mess. That's no fun. And it's, in addition to being not fun, I just don't know how meaningful it is. All right. let's pause. I want to make sure that I have what I need to describe this next theorem for you. Let's pause. We'll come back shortly. Mean value theorem for integrals. Just look at this, and I'm hoping the GeoGebra worksheet is going to make sense to us, or help us make as much sense as we could out of this. If f is continuous on a closed interval AB, then there is at least one number c in the closed interval such that the value of the integral is equal to, oh, we still need a picture for this, a to b. There's our interval. And imagine the picture looks something like that. So there's a, and there's, well, f of a, and there's f of b. So the value of the integral is going to be the area, since it's all positive here, the area bounded by the curve and the x-axis. That's the value of the integral. What we're saying, if the function is continuous, is that there exists a number c in here such that if we take this distance, okay, from a to b, it's b minus a. That's how far that is, b minus a, from there to there. If we take that and multiply it by the function value, it's going to equal that total area. So basically, I'm visualizing a rectangle. And I'm wondering where it would have to be. I'm just going to have to guess at this a little bit. How about there? I don't know. If I draw a rectangle like that and consider the area of that rectangle all the way down here, all the way down here, all the way over there, is that going to be less than the value of the integral or more than the value of the integral? The area of that rectangle. A little bit less. Yeah, I'm concerned about this region. It might be less than the area of that. So should I go a little higher? Let me go higher. What if I go up there? How about now? Does it look like it's equal? Maybe so. And if so, then what we're saying is this is the value c. So that if we evaluate the function, this is the point c, f of c. So the distance from there to there is f of c. So if we take f of c and multiply it by b minus a, we get the area of that green rectangle. And we're saying because the function's continuous, there exists a number c that gives us a point on that graph that makes it happen. If the function's not continuous, what can happen is this. Maybe the graph does that and maybe picks up right there, and there's no particular value where we can evaluate the function and say, let's multiply that function value by the length of the interval, and that will give us the value of the integral. So because it's continuous, it makes it happen. I'm just going to glance at this a little bit and see the area under the curve is 22.5. I want to see if we can somehow come up with the value of c that'll do this for us. Looks like we need to go to the left somewhere. Maybe right there. Is the area of that rectangle approximately equal to, and let me get this out of the way. The area of that rectangle, is that approximately equal to 22.5, you think? The same as the area under the curve? Or should the rectangle be taller or not quite so tall? What do you think?
I think it's good.
You think it's good? Okay. Let's see about what this area is. So if I take B and go up, 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 up. Is it good? Maybe come back down. No, I guess up a little higher. 22.5, I guess, would be about right there. So maybe I should go right there. Yeah, I want to call it 3.84. 3.84 looks like it'll work. It looks like that's the value of c in this interval. such that if I evaluate the function at 3.84, that gives me the height of the rectangle, and if I multiply that by 3, which is the base of the rectangle, that's going to equal the value of that integral on this interval here. So it looks like about 3.84 is the value of c that the mean value theorem for integrals is telling us exists. I should have inserted an extra page. There we go. Is it going to ask for... Yes, it is. Find the value of c in the interval 2, 5 for the function f of x equals x squared, whose existence is guaranteed by the mean value theorem for integrals. Typical test type question. Let's see if we can find it. Oops. And to scroll this one down. Well, I want the integral from 2 to 5 of x squared dx to equal f of c times 5 minus 2 for some value of c. That's what I want. If I'm thinking about what the graph looks like, 1, 2, 3, 4, 5, maybe 5, 10, 15, 20, 25. At the point 5, 25 right there. At the point 4, 16. 4, 16 would be about right there. 4, 16, and 3, 9. About right there. And 2, 4, and 1, 1. Primarily interested in what's going on between 2 and 5. Right there's 2, and right there is 5. So we're thinking area bounded by the curve. All right. The rectangle is going to have a base of 3. Let's go orange for the rectangle. Base of 3 and a height of, well, we could calculate that, right? Well, I guess we need the area. Area bounded by the curve. Is it going to be about that high? Or should it be higher? Or lower? Is that too high? About the right height for the rectangle. So what we're looking for is the value of c. What is the number where we can evaluate the function there? That'll give us a point on the graph, and we can multiply that function value by 3. And that'll tell us the area under that curve. Well, we can find it. It's just algebra at this, well, it's a little bit of calculus, I guess. Antiderivative of x squared, we've been there, we've done that. X cubed over 3. We're going to go from 2 to 5. F of c equals c squared. And we're going to multiply that by 3. So this is 5 cubed over 3 minus 2 cubed over 3 equals 3c squared. (125 minus 8 equals 3c squared. 125 minus 8, 117 maybe? So I want to say, is that right? 117. C squared equals 117 ninths. If I divide both sides by 3, maybe 3c squared is 117 thirds. C squared equals 117 ninths. And 117 has got to be divisible by 9, because 1 plus 1 plus 7 is 9, which is divisible by 9. So 9 goes into that 13 times. So c squared equals 13. C is the square root, the positive square root of 13. That's, what is that? 3.6? Here we go. So I was a little bit too far to the right there. I drifted just a bit. So something like that. Maybe the rectangle was too high. But yeah, about 3.6, that's where we want to be. And if we evaluate the function at the square root of 13, we get 13, because we take the square root of 13 and square it. This is a squaring function. We get 13. So if this is going to be 13 from there to there, and this is going to be 3 from there to there, is it 3? I'm worried. Should I worry? Maybe I shouldn't worry. Because the total area is 117 thirds, right? 117 thirds, which is, what's 117 thirds? Is it 39? 39. So there we go. That's the area of the rectangle. 13 times 3 is 39. So the area bounded by the curve in the x-axis is 39. Area of the rectangle is 39. So to answer the question, C equals the square root of 13. That's what we were looking for. That's the value of C between 2 and 5, whose existence is guaranteed by the mean value theorem for integrals. Now, the fundamental theorem of calculus part 2 is important enough, but I've actually skipped something that's kind of important, and so I wanted to make sure that I include it. So what I could do is copy this and paste it down here. The average value of a function. This is really closely related to the idea of the mean value theorem for integrals. If f is integrable on a closed interval a to b, then the average value of the function is basically this. It's what we get when we find the total area bounded by the curve in the x-axis and divide by the length of the integral. The length of the interval. The length of the interval. So maybe look at the one we just had and see if it makes sense to call this the average value. What we just looked at was this, and if we take 39 is the total area bounded by the curve in the x-axis, and divide it by 3, we'd get 13. So what we're saying, this function on this interval starts out at 4. Somewhere along the way it's equal to 9. Somewhere along the way it's equal to 16. Somewhere along the way it's equal to 25. If it only took on finitely many different values, then we could see how long it was equal to each of those values and come up with a weighted average. But it's a continuous function, takes on infinitely many different values. But what we're saying is, on average, this function is equal to 13. Does that make sense? If I said, on average, this function is equal to 1,000,000, that wouldn't seem quite right, would it? That seems like a bit much, since it never actually is equal to that. But if I said, on average, it's equal to 13, how do you feel about that? Does that seem like a meaningful way of calculating the average value of this function?
So you like mean on like different parts, like you went up from like 5 to 8. On average, it would be equal to 13 there?
No. If we just did the calculation, say, on this little interval between 4 and 9, on average, I would say it's maybe equal to, what, 5 or 6? 6, 7, maybe, something like that. On that little interval, I would say on average, it's equal to about 7. Somewhere between 4 and 9 would make sense. But on this entire interval, I think the natural thing, the way to define this average is to think of what's the total, I don't know, total what? Total area is what it is. But how do we measure the value of a function if it just took on finitely many different values? Then we could kind of give each one a weight of 1. But how do we assign the weight? We had to think, okay, how long is it equal to this? And not very long, and then multiply by the length of the little subinterval. Some sort of limit involved. But I think a very natural way to do it without having to think too hard about the calculus that goes into it is that the total area bounded by the curve is equal to 39. And the length of the interval is 3. So if we divide 39 by 3, on average, this function is equal to 13. I think it takes into account not only the values it takes on, but how long it takes on those values. So that's how we define the average value. We find the total area. Actually, it's going to be not the total area. This is going to work both for positive f's and negative f's. The net signed area. The net signed area. And then divide by the length of the interval. This is the average value. So if I wanted to find the average value of a function, well, I just did, but find the average. Oh, let's find the average value of a linear function. Find the average value of f of x equals 2x plus 1 on the interval from 2 to 6. One, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12, 14. So at 2 it's equal to 3. And at 6 it's equal to 13. So that's the point 6, 13. That's the point 2.
2 wouldn't be equal to 5.
Put that too high, didn't I? Where's 3, right? If this is 2 and this is 4, 3 would be about right there.
Would it be equal to 5?
2 times 2 is 4 plus 1. So I had the point in the right place. I was just thinking the wrong thing. There we go. That is 5. Thank you.
I was really confused.
So my geometry was okay, but
Oh, no.
my algebra was ridiculous. There we go. Yeah. And 2 times 6 is 12. 12 plus 1 is 13. I did have that one right. Okay. So there we go. So it's equal to 5 when it starts out, then it's equal to 13. So on average, it's equal to what? Is it going to be 9 on average? Let's hope so. It's going to be 1 over 13 minus 5 times the integral from 2 to 6 of 2x plus 1 dx. We're going to hope we get 9 out of this. This is 1 over 8 times, okay, we need an antiderivative. How about x squared plus x? Take the derivative of x squared, you get 2x. Take the derivative of x, you get 1. So x squared plus x ought to work. Go from 6 to 2. So this is going to be, maybe put it up here, 1/8 times, it's going to be 6 squared plus 6. Maybe I should use brackets instead of parentheses. Minus 2 squared plus 2. So it's 1/8 of, or parentheses. Yeah. 36 plus 6 is 42. So it's 42 minus 6. So it's 1/8 of, I'm worried. What did I do? 13 minus, oh, dummy. 6 minus 2. I get in a hurry, I get excited, I'm sorry.
You're losing us. 6 minus 2 is the interval.
It's the interval, yeah. Divide by the length of the interval. Oh.
Everything else right?
Everything else is right. Yeah, except for that. What's the fourth of 36?
9.
It's 9. Ah, there we go. Yes, 6 minus 2 is what? The length of the interval. That's what we divide by. So the total area is 36. And we divide by that 4 there, so on average this is equal to 9. It's the average value of the function. Fundamental theorem of calculus, part 2. Fundamental theorem of calculus part 2. If f is continuous on an interval I, then f has an antiderivative on I. Well, much can probably be said here. If a function is continuous, does it necessarily have a derivative on an interval? If a function is continuous, like the absolute value function, it's not necessarily differentiable. But if a function is continuous, the theorem says that it does have an antiderivative. Turns out that having an antiderivative is easier than having a derivative. It's a weaker condition than having a derivative. So if f is continuous, then it has an antiderivative. In particular, if a is any point in an interval I, this particular function, as it is defined here, is an antiderivative of f. That is, if we were to take the derivative of this function, defined by this integral like this, we would get little f of x. So what we're saying is derivative of this function where x, the variable, is in the upper limit of integration. This is equal to f of x. So maybe just what the function looks like. I was trying to come up with an example. There's something weird that GeoGebra does. Oh yeah, save it. Wait a minute. Open it. What I've called it. Integral from 1 to b. I've got the b right there. I tried to put a number there, but it didn't want to put a number there. It would only give me one digit, and it put the decimal part somewhere else. So here's the number b. If b equals 1, basically it's the integral from 1 to 1. And there's no area at all. If b equals 2, it's the integral from 1 to 2, and it calculates what the area is. The definite integral is the integral from 1 to 2. This is the function right here, the cubic function. You can tell the shape there. It's a cubic function. And it's giving us the area. So the function that we're talking about that would have this as its derivative basically is this. Big F of x equals the integral from 1 to, I'm going to say x of x cubed minus 9x squared plus 23x minus 7. Oops. And I always do that. Those variables are not allowed to match. Let's do this. T cubed minus 9t squared plus 23t minus 7 dt. If I take the derivative, big F prime of x I get x cubed minus 9x squared plus 23x minus 7.
For t, right?
Well, I have t's right here. T there, and a t there. The process of taking the derivative, basically what happens is, since it's a function of x, what we get is this same expression except with x's replacing the t's. What it's saying is, we have to think what the derivative tells us. Limited amount of time in which to think this. The derivative tells us the rate at which a function is changing. And the rate at which this, since the function is defined to be the integral from somewhere to x along here, and we're wondering how is that total amount of area changing. Well, if the function is very large, then a little increase, I've got to erase that, but a little increase is going to increase the area by that much. If the function's not as large, a little increase will increase the area by not quite so much. So basically, the rate at which this area function is changing is the function itself, the curve. And if you want to assign numbers to it, I see the clock, it's ticking. If you want to assign numbers to it, the value of the function is 11 right here. I think it is. Better mouse. The value is 11. The total area is 10.25 for the green. Suppose I take a tenth of a step to the right. We would expect the total amount of area to increase by well, 11 times that 1/10. So we'd expect the area to increase by about 1.1. So if I go from 2 to 2.1, I go from 10.25 to what? 11.3 something maybe? Yeah, 11.3 something. So we're asking ourselves, how fast is the function changing? Well, its rate of change, the area function, the rate of change of the area function is the curve itself. So if we're at 4, this one I think is kind of interesting. We're at 4, the value is 5. The value of the function is 5. If I take a step 1 unit to the right, I would expect, well, if I take a step 1 unit to the right, I would expect it to increase by 5. But if I take a step just a tenth of a unit to the right, I would expect it to increase by 0.5. So it goes from 26.25, and this one I think it does exactly, to 26.75. So it's the area function that we're talking about when we define the integral from 1 to x, f of t dt. But the derivative of that is the function itself, because the function itself is the rate at which that's changing. It's a tough thing to talk about right at the end of class.